Hello, how are you guys doing? I thought I'd put my camera on just so you could see my face a little bit since I think I've only done maybe one of these headshots and this is day number 4. So I hope things are going well for you guys out there. And our plan today is I'm going to go through a very short, easy topic. We've had kind of some really tough ones. Structural diagrams, shape diagrams, being able to draw those is pretty tricky. And it's certainly hard when you can't get your questions asked right away like you could in class. So hopefully you're able to get through those all right. And today we're going to be looking at intramolecular and mainly intermolecular forces that are happening between molecules. I'm going to get you set up so that you will be able to do an assignment for me tomorrow and hand it in tomorrow. So that's coming at the end of this lesson. So hopefully you're doing well and staying on top of things. I'm just going to close this off and let's rock and roll. So intramolecular forces, intermolecular forces. The words kind of say it all. Intra is Greek for within, and inter is Greek for between. So these are forces that are found within molecules or between molecules. So let's take a look at this diagram where we have a positive sodium ion in the middle, and it is attracting 6 water molecules around it because you know that water molecules are polar. Because of the bond dipoles, they all have a negative end and a positive end, and it's the negative side that's attracted to the positive sodium. So do you think that is a force within a molecule or between molecules? Okay, and how about this one? Methanol and water, which are both polar molecules. So methanol, this would be its positive pole, and this is water's negative pole. Do you think that's a force within a molecule or between molecules? Okay, and then our third example is hydrogen, H2, and they are sharing their valence electrons. Do you think this attractive force between these two atoms is intramolecular or intermolecular? So if you guessed intermolecular, intermolecular, and intramolecular, you would be correct. Okay, a few more examples. This is CH4, drawn as a structural diagram, looks like that. The force that attaches the hydrogens to the carbon, intramolecular or intermolecular? And the force that is attracting these neighboring molecules, this is the negative side of the acetone attracted to the positive side of hexane and octane and hexane over here. So these are intermolecular forces, and they're actually specific types, what we call dipole-dipole and London dispersion, and we'll go through those in our lesson today. So let's rock and roll. Okay, intramolecular forces, those found within a single molecular unit. And there's 3 types that you have to remember. Metals have intramolecular forces. Ionic compounds have intramolecular forces. And so do covalently bonded molecules, intramolecular forces. The metallic one is a little strange. So when we talk about a metal or a chunk of metal, let's say this is a block of metal, B-L-O-C-K. Ugh. That is just ugly. So in a block of metal, they do some strange things. The metal atoms actually share their electrons between them, and you treat this as one big single unit. And I think we talked about this at the start of the chapter, how in a metal you have a sea of electrons that is being shared. And so we call this intramolecular because it's like one giant molecule of many metal atoms. So that one's a little tricky to get your head around. Easier ones are covalently bonded molecules like hydrogen and oxygen and water and methane, where they are clearly sharing their or attraction is within the molecule. So these hydrogens are bonded to the oxygen by a covalent bond or a molecular attraction within the molecule. And the same with ionic compounds. We say that the Na plus and the Cl minus, which form one unit, are attracted by a force within the molecule. The positive sodium is attracted to the negative chlorine, making the ionic bond, which is also within a molecular unit. So 3 examples of intramolecular. Now, where we're going to spend our time today is on intermolecular forces. And if you're in my class, you'll have some study notes for this. And if not, you might want to put these examples down on a sheet of paper or save this lesson to refer back to. So intermolecular forces between molecules. So what's going on here? These are the forces that help determine the properties of a substance. So for example, whether it is a solid, a liquid, or a gas at room temperature or at SATP, standard ambient temperature and pressure, that can be predicted by the intermolecular forces. And so can boiling point, melting point, freezing point, evaporation, boiling, condensation. All of those changes of state are determined by the strength of the intermolecular forces. So what do you think the answer to this question would be? The stronger the intermolecular force, the higher or lower the boiling point. So if you have 2 molecules and the intermolecular force or the attractive force between them is really high, will they jump into a gas and separate with low energy or high energy? In other words, will they have a low boiling point or a high boiling point if there is a high strength of attraction between the 2 neighboring molecules? And the correct answer is the stronger the intermolecular force, the higher the boiling point. And we're going to be looking at 2 intermolecular forces today, dipole-dipole and London dispersion. Okay, hydrogen bonding we will save for next class. Just to give you an idea of what hydrogen bonding looks like, these are all water molecules. And they are all being attracted to their neighboring molecules with an intermolecular force that we call hydrogen bonding. The negative pole of the water is attracted to the positive of this. The positive of this is attracted to the negative. So every negative pole is attracted to the positive pole of the neighboring molecule, creating this pretty strong intermolecular force that we call hydrogen bonding when it's in water. Okay, I think what I'm going to do here is just pause for a second. I want to show you guys this FET that I've loaded up. I've given you the link to this one so you can check this one out and play around with it on your own as well. So this is neon gas, and neon has really low intermolecular forces. In other words, it doesn't take much energy to get it into a liquid. I'm just going to change the energy to degrees Celsius from Kelvin. So this is neon at minus 259 degrees Celsius. If I want to melt neon into a liquid, we need to heat it up to a whopping minus 246. Now, if you look at the molecules, you can actually see their behavior, that they are kind of sticking or attracted to each other. Occasionally they separate out, but they tend to come back towards each other and they're almost attracted. There's a stickiness to them as they suck to their neighboring partner atoms. Now that's at minus 246. If we flip to argon, argon has stronger intermolecular forces, and you have to heat it up to minus 187 in order to get it into a liquid. If we go back to argon as a solid, it's a solid at minus 230. Why does it stay a solid? Because the atoms are sticking to their neighbors due to their intermolecular forces. Heat it up from minus 230 to minus 187 and we get a liquid. Okay, what about a gas? How much more energy do we have to add to separate these molecules so they're all in their gas phase? Heat it up from minus 187 to minus 84. That's enough energy to spread these out and overcome the intermolecular forces and have them as a gas. And you can see as they approach each other, they still kind of stick together until they get knocked by a neighboring atom and jarred loose. If we go to oxygen as a solid, okay, there it is at minus 246, heat it up to minus 216 for a liquid, and then minus 160 for a gas. So oxygen has higher intermolecular forces than neon and argon. You'll also notice the shape of the molecules. This is O2, it's diatomic. So each oxygen molecule is 2 atoms of oxygen. And if you watch them, you can see how they do temporarily stick to their neighbors until they are knocked loose or jarred by another molecule, freeing them up. Now, water, H2O, you can see the shape of the molecule. And water has this unusual intermolecular force called hydrogen bonding that is quite strong as far as intermolecular forces go. This is water as a solid. It's the only substance on Earth whose solid is less dense than its liquid. When we heat it up and get it into its liquid state, it takes up less space. And you can see the water molecules acting strangely because of their positive and negative poles, bouncing around, spinning, attracted to their neighbors, positive side to the negative side of the next. And that's that hydrogen bonding. And this is a liquid at 13 degrees Celsius. And water has an extremely high boiling point. Here it is at 156. It's already well past its boiling point and into a high energy gas. So I want you to pull out this FET later on, play with it, try these. You can go into phase changes. There's all kinds of stuff that you can manipulate if you want. But the key one is really the states of matter and just seeing those intermolecular forces. Okay, so the first one that we're going to look at is dipole-dipole, which is a fancy way of saying that you have a polar molecule and another polar molecule, or 2 poles. So we've got a positive and a negative, a positive and a negative. And you know that any polar molecule, so anything that has a bond dipole, so for example, HCl that's drawn up here, the chlorine has very high electronegativity. So if we drew in a bond dipole, it would look like that, pointing to the chlorine with its high electronegativity of 3.2 compared to hydrogen's 2.2. So what that means is UG 2.2. The electrons spend more of their time around the negative chlorine, less of their time around the hydrogen. So there's not a lot of electron density here. Most of it is on this end, giving us our negative pole, a positive pole. If we park one of these HCl's against a neighboring HCl, the positive side of this one, which is the H, goes to the negative side of this one, which is the Cl. So the molecules literally align themselves so that the negative pole of one is attracting to the positive poles of its neighbor. This positive pole is attracted to the negative poles of its neighbor. I suppose I could color code those. So this positive attracts to those three negatives. This positive, where's another good example? This negative is attracted to these two positives. So all of these dashed lines are representing these intermolecular forces between the two poles or the dipoles of each of these polar molecules of HCl. In word form, they say a dipole-dipole force occurs in polar molecules due to the simultaneous attraction between the dipoles of the molecules. Oppositely charged sides attract, and in a liquid, the molecules can move and rotate to allow the strongest attractive effect or maximize attractions, minimize repulsions, and you get a strong overall attraction in the liquid state. Okay. The second intermolecular force is called London. I have no idea how to get rid of that. Let's try that. Okay. So the second intermolecular force, or London forces, is a weaker one. Weaker than the polar or dipole-dipole. And it's really just due to the electrons that are hovering around the valence of a molecule, or all of the electrons. So the example that I'm going to show you here is an individual atom, and it has all of its electrons. Let's pretend that this atom has 4 electrons. If by chance, at some point in time, all 4 of its electrons are on the left side of the atom, that creates a positive pole on the right side. So this is what we call a temporarily polar molecule. Just for a brief moment in time, the electrons happen to be on the left side, creating a negative charge and a positive charge. And it's only temporary, so it's called a temporary dipole. Now, what this will do is, if there's a neighboring molecule, a second one, and it comes close to the first one, the positive poles on the right will attract the negative electrons in the second molecule and pull them all to this side and make this one also polar or temporary. So what it does is it creates temporary dipoles in the surrounding molecules. These things all get these temporary poles to them, a positive side and a negative side. If this one approaches the neighboring, it will make this side positive and this one negative. And so the opposites attract, and you get these temporary attractions, or London dispersion forces. Okay, that's lots of theory. Now, the key idea to this is the more electrons you have, the stronger the London force. Okay, and this only applies to non-polar molecules. I shouldn't say it only applies, but it's the only force present in non-polar molecules. Okay, so how do we use this stuff? All right, so if you know London forces, or you can, you know the number of electrons, you can predict the strength of London forces. So we have 4 molecules here, and they all have the same shape. They're tetrahedrals. So they are going to look like this, with our into the page and our out of the page. Okay, CH4. SiH4, exact same thing, except it's silicon in the center and germanium in the center and tin in the center. So shape doesn't affect these. They're all nonpolar. So the only intermolecular forces they have, the only intermolecular forces are London dispersion. So what does that mean? Well, if we know the number of electrons that are in the molecule, you can predict the relative size of the boiling point. More electrons, stronger intermolecular force, higher boiling point. So which of these four would have the highest boiling point? Looking at number of electrons. And if you guessed SNH4, you are correct. So what is its boiling point? Well, it's minus 52 degrees Celsius. Okay, which one would have the next highest boiling point? 36 electrons, minus 89, minus 112, minus 164. Now, if you look at these, you go, holy crap, those are really low. These things have crazy low boiling points. Yeah, they do, because they have a very weak intermolecular force. They're nonpolar. All they have is that temporary dipole attraction between neighboring molecules. It does not take much energy to get them to separate into a gas or boil. So all of these boil. So at room temperature, all four of these things are gases. They've all boiled. Anything warmer than minus 50 and they are boiling into a gas, which is kind of crazy. Okay, almost done. So now here we've got four more molecules. They are all hydrocarbons, tetrahedral. So methane, if I just did it as a quick structural diagram, it looks like this, CH4. It is a tetrahedral. Ethane is 2 carbons with 6 hydrogens. Propane is 3 carbons with 6 hydrogens. And butane is 4 carbons with 10 hydrogens, 10, 8, 6. Okay, so which of these four molecules would have the highest boiling point? Which one would have the lowest boiling point? Because they're all nonpolar, we only have to worry about number of electrons. So you count them up. Carbon has 6. Each hydrogen has 1. So this is 6, 7, 8, 9, 10 electrons. Ethane, 6, 12, 13, 14, 15, 16, 17, 18 electrons. Propane, 6, 12, 18, 19, 20, 1, 2, 3, 4, 5, 26. And butane, I'll let you figure that one out. Okay, so now you know the number of electrons. You can predict their boiling points. Butane will be the highest, most electrons, strongest temporary dipoles. Methane will be the lowest. Okay, so what are the boiling points of these? Methane is a very small molecule, 10 electrons. That's a pretty low London dispersion force, minus 162. Ethane is minus 89. Propane minus 42. And butane is minus 0.5. If your vehicle runs on propane gas, if the air temperature is colder than minus 42, less than minus 42 degrees Celsius, your car won't run because the propane stays as a liquid and the liquid does not work in the engine. It needs to be a gas. So that's why on really cold days, the school buses can't get started if they run on propane, so they cancel school for the day. Okay, hopefully you have no questions on this slide. This is all nonpolar molecules, London forces, total number of electrons, and you can put them in order. I would not ask you to give me the boiling points, just lowest to highest, put them in order. Okay, let's take a look at these two molecules. They're isoelectronic. Iso from math, isosceles means same angles in a triangle, and iso means same, electronic, so same number of electrons. Okay, so both of these molecules have 70 electrons. So based on London dispersion forces, they should be the same boiling point. Okay, they have the same number of electrons, so they should have the same boiling point, but they don't. ICL is higher. Why? Okay, so that means there's another intermolecular force at play, which we already talked about, and that is the, whoops, and okay, my apologies. A screen popped up. I have no idea why, and it's now gone. All right, so why is it higher? Because ICl is a polar molecule. Chlorine has higher intermolecular forces than iodine. So if we draw our dipole arrow in, this is the negative pole, this is the positive pole. So because it's polar, we have dipole, dipole. Intermolecular force plus London dispersion forces. So when you look at this difference, 59 to 97, we're looking at an extra 38 degrees Celsius bump. So it is 38 degrees Celsius higher, and that extra is due to the dipole-dipole forces. They both have the same electrons. They should both be 59 degrees Celsius. The polarity of this, the permanent, so that is permanent, not temporary. London dispersion is a temporary dipole. Temporary dipole, I apologize, my printing is terrible. So because it's a permanent, stronger intermolecular force with those permanent dipoles, you get an extra 38 degrees Celsius. All right, so in your textbook, there's 5 questions to do. Okay, they won't take very long. It's a pretty small lesson. The second thing I need you to do is using your phone, you need to practice taking a photo and then convert it to a PDF file, because that's how you're going to be handing in your homework assignment and you're going to be getting from me tomorrow. And I'll have some details on that as a separate document in this lesson on how to find a free app that will let you convert photos to PDF so you can hand in an assignment to me that you have written out on paper and taken a picture of. Okay, that's it for now.